Second-order nonlinear optical processes are at the heart of modern photonics, underpinning a remarkable range of technologies. For example, X-ray free electron lasers, among the most powerful light sources ever built, produce intense X-ray pulses used to study matter at the atomic scale. Those X-rays are generated from an accelerated electron bunch that begins its journey at the very start of the facility, the photoinjector. Here, a precisely controlled ultraviolet laser pulse strikes a photocathode to liberate the initial electrons. These systems rely on a cascade of nonlinear processes to produce shaped ultraviolet pulses, including second-order processes like noncollinear sum-frequency generation. Accurately simulating this nonlinear frequency conversion in the full laser system can be computationally expensive, a bottleneck that grows more critical as facilities push toward autonomous operation and digital twin development.
This is where we work, the photoinjector laser lab. Conventionally, simulating the nonlinear optics in our system involves solving the nonlinear Schrödinger equation with a split-step Fourier method, propagating through the crystal slice by slice, alternating between time and frequency domains. This is accurate, but it can also be slow. For instance, if you want to run an optimization loop where you have 1,000 iterations of the simulation, or you want to loop it into a start-to-end model of your facility, the timing here becomes a hard constraint. Borrowing from machine learning developments in the fiber optics community, we've developed a long short-term memory model as a surrogate for these second-order nonlinear processes, specifically trying to mimic how the fields propagate in this crystal slice by slice, and doing so in a reduced frequency space. The network is trained on high-fidelity split-step simulations spanning a wide range of pulse shapes, and it reproduces the evolution orders of magnitude faster. Running on a GPU with batched inference, average simulation time drops to the single-digit milliseconds compared to nearly 2 seconds of the conventional solver. The model accurately reconstructs both the temporal and spectral profiles of the output fields across a wide range of pulse shaping conditions. This surrogate model is designed as a modular building block, one piece in the larger start-to-end model of the laser system. But long-term goal is a genuine bidirectional information exchange where simulation and experiment are informing each other in real time towards a true digital twin of the laser system and beyond.